All right. We're going to deal with continuous electrostatics today as part of our review. So again, packet and solutions are in the description. So we're going to continue with 17, which is an equipotential problem. So we're given the different potential values along different curves, and we're going to be asked to analyze this. So first, we're going to ask to draw some electric field vectors at each of these labeled points. So we have two rules for drawing equipotentials. So first, we know that the electric field lines always have to be perpendicular to an equipotential. And then we also know that it has to point downhill. So you have two options as to what perpendicular to draw. We always draw the one that takes you downhill. So maybe we can start in and go out. So point D, that's at my tallest height. It's at 70. So again, it's going to get pushed directly downhill. Same thing with C. Trying my best to draw a nice perpendicular at each of the points. So it's going to be perpendicular to the equipotential curve. And there we'd have our four little field vectors here. Because again, it represents the direction that a positive charge would go. And positive charges are pushed downhill in terms of the potential. So the electric field is like perpendicular to the equipotentials, also called isolines, and it points downhill. So now we're just going to look at a possible charge distribution that could generate these lines. So notice the height is really, really strong near where these sort of gaps are in the middle. And we said that positive charges generate hills and negative charges generate valleys. So we're seeing only positive heights here. And we see that it's really tall towards the two center points. And it's actually, the field lines, the equipotentials are closer together near this left charge. So it actually have two positive charges with a greater magnitude charge on the left. So that would be our possible charge distribution here. It's just two positive point charges. And then at which of the points is the field the greatest? So we have the relationship between field and potential that tells us that the magnitude of the electric field in a certain direction, let's say x for example, would just be equal to the magnitude of the rate at which potential is changing in that direction. So we can estimate that the magnitude of the E field is roughly the change in volts divided by the change in distance. So it's sort of a slope of the potential, as we said before. So we're ranking E field magnitude just based on the spacing, where the closer spacing has stronger E field because you have the same drop over a less distance, because all of these are spaced by 10. So you could argue other ways that D has the strongest field without using the E field being stronger with close equipotentials argument. Like you could clearly see that point D is closest to this really strong charge, so it should feel the biggest force, but the spacing approach is probably your best way forward. The lines are spaced closest at D, so the field is the greatest at that location. All right. Now we'll look at an electron placed at B. So if I place an electron at B, it will not go up and to the left like the field is showing, because that's what a positive charge would do. So the electron would accelerate uphill or against the electric field. So it would actually accelerate sort of downwards here. So the electron would accelerate downwards opposite the field, or at least it's roughly downwards. It just needs to accelerate near to the closest potential that's higher than 40 volts. And now we had a typing error, which is why the formatting is all messed up on this question. A particle with mass given and negative charge is placed at point A. What's the speed upon reaching the 40-volt curve? So we always use energy conservation with these equipotential curves because it's inherently telling us to use energy. So we use the fact that the change in kinetic energy, delta K, is equal to the negative of the change in potential energy, U. And change in potential energy for a point charge is always Q times delta V. So now we could write that the change in kinetic energy, which would be the 1/2 square mv squared that the particle ends with, minus the 1/2 mv squared the particle starts with, has to equal minus Q times its final potential value minus its starting potential value. And we're given that it's placed at point A, which is 30 volts, and then the electron accelerates to 40 volts. Well, it's not an electron, it's negatively charged, so we know this will speed up because it's going uphill. We're also given it's released from rest, which is always nice when we can cancel out our initial kinetic energy term right here. So now we could just solve this. So I'd multiply both sides by 2, divide by m, take a square root. I would get Vf, the final velocity, is square root of negative 2 times q times the final potential minus the starting potential divided by the mass of the charge. And it might seem problematic that we have a negative in our square root right now, but that's no issue because we also have a negative charge. So now working everything out, we get negative 2 times our charge, which was also negative 2, but microcoulombs, so we can't forget the 10 to the minus 6 here. And then we have our change in voltage. So our voltage went from 30 to 40. So I would give myself a 40 minus 30 as my change in voltage. And then the mass of the charge was given to be 2.5 times 10 to the minus 8 kilograms. And remarkably, working this out, we actually get a whole number answer of 40 meters per second. And notice we didn't actually have any sign issues in this problem because we had a negative in the square root, but there was also a negative charge and a positive change in potential. So everything worked out nicely. But chances are if you do the whole problem and you get a non-real answer error, you probably forgot an extra minus sign, either by you forgetting the fact that delta K is negative change in U or forgetting a sign of the potential difference, perhaps. All right, now we'll go for the field potential relationship. So the electric potential along the axis is given by this function. What's the x component of the field? So it's a fact on the sheet that since the field is the slope of the potential, we could write this sort of derivative relationship where the electric field is just the derivative with respect to whatever coordinate you want. Because again, we said that the field points downhill in potential, and downhill means the negative slope. So that's exactly why this is the formula. Don't forget the minus sign. This is a very common multiple choice, and they will include the version with forgetting the minus sign. So this is just a simple derivative. It's 2ax. And then since it's in the x direction, I could give myself an I hat, but the I hat is definitely implied in this problem. It's in the x direction. Suppose a positive charge of mass m and charge q is placed at x equals c. How fast is the charge moving from rest after it passes through x equals 0? So I'll actually use the same technique as in the last problem, where we'll use the fact that the change in kinetic has to be opposite the change in potential, which would be negative q times delta v. So once again, we could write our left side as the same, where we have 1/2 mv squared at the start, or sorry, at the end, and subtract off the, well, this will be 0, 1/2 mv squared at the start. But here we actually have a potential function to evaluate. So for our potential function, we're given that it starts at x equals c and then ends at x equals 0. So I take the potential at x equals 0 as my final potential, and I take v of x equals c as my starting potential. And I have a function here that I can use for this. And again, just plugging everything in and using the fact that once again we do start from rest, so I can just cancel my initial kinetic energy term. I'd get 1/2 mvf squared is equal to negative q. And again, no sign things here because the charge was just defined as q, not minus q, so I just carry that sign over. And then v at x equals 0, well, if I just plug in 0 to ax squared plus b, I get b. And then if I plug in c to ax squared plus b, I get AC squared plus B. And I have to make sure to subtract off that entire thing. So then, another simplification, we'd get 1/2 mvf squared is equal to, well, the b's are going to cancel, which makes sense because potential is defined up to a constant. So I'd get a negative q times a negative AC squared, so I'd get q AC squared here. And now we see that the sign issue resolved itself, and it should make sense that our change in kinetic energy is a positive number, because it will speed up. Because what this potential graph looks like is the potential graph was like a quadratic, so it looked something like this. So I would be accelerating downhill if I started at some point and then went through the origin. So then it's just a simple rearrangement to solve for VF, which is just the square root of 2QAC squared divided by M. And lots of letters there, but there's our final answer. All right. Well, now it's time to start getting into the Gauss's law adjacent things. So first we have the conductor nest, the classic, where we have a charge in a cavity, and we're going to look at how the charges in the shell rearrange. So first we want the charge on each surface. So it is guaranteed that in any of these systems where you have the conducting shell with thickness, there must be zero field, not potential, zero field inside the conducting shell. So for that to work, there has to be no net charge enclosed whenever you're inside the shell. So by working that out, you see that no matter what, you always need the inner surface of the shell to hold charge that will cancel what it sees in the cavity. So I am actually guaranteed that in every single one of these conducting problems with the shells, the inner shell will always hold the opposite of the cavity charge. And if you have nothing in there, it's zero. But here we have a minus q, so for the shell to cancel it out, we know my inner surface has to hold a plus q. And then there's two ways of doing this, the second part. So my inner surface would be plus q. And then there's two ways of doing the outer surface. There's the long way, and then there's the easy way. So for the easy way of doing the outer surface that avoids having to explicitly use conservation of charge, we know that the net charge of the system right now, as I drew it, is zero, because I have plus and minus q. So that must mean that the outer surface holds the system's net charge. So it is always true that the outer surface holds the net charge of the system. And the net charge of the system would be the minus q that's held inside the cavity, plus the minus 8q that's held in the shell. So that would be minus 9q. There is an alternate approach to doing this that might make this a bit more clear. You could have equivalently wrote the equation that says the shell has negative 8q total, and it gets to pick how it distributes that minus 8q. So it's going to distribute part of the q in the inner surface, and then it's going to distribute part of the q in the outer surface. And we were guaranteed, due to the electric field being zero in the conductor, that the inner surface had to have been given plus q already in order to shield the inside of the conductor from the effects of the minus q inside. So we can see that I just subtract a q from both sides, and I would get the q of the outer shell would in fact be negative 8 minus 1, which makes negative 9q. But I always say just do the shortcut, that the outer surface has to hold the net charge of the system, because the inner surface will always cancel what's going on inside, which means that all your net charge has to go to the outer surface, because this is effectively zero net. All right, find the electric flux. So whenever we actually want to find the flux, it is quite easy, because we don't want to find the electric field or anything. We don't have to use Gauss's law here to actually find the field. Just find the electric flux. So when we see the word flux, we could calculate flux from the integral definition, integral of E dot dA. That is one way of calculating electric flux. But why would we do that when we have Gauss's law, which says that the flux is also found just by taking the enclosed charge and dividing by epsilon naught. So that's all we're going to do, is just find the enclosed charge in each of these regions and divide by epsilon naught. So for the first one, we just have minus q enclosed. So our flux would be minus q over epsilon naught. Then for our middle region, where we're enclosing the minus q and the inner wall, well, notice I enclose a q and a minus q. So the flux would be 0 in this one. And then the entire system. So if I enclose the entire system, I'm enclosing a minus q and a plus q, which makes 0. But then I'd also be enclosing the minus 9q, which is the net charge of the system. So I would enclose the net charge of the system when I'm looking outside, which is minus 9q. So there's our 3 flux values. And if we somehow use the expression of E from a point charge and actually multiplied that by the surface area, in each case, you would actually get the same thing, but I don't know why we would do that. So now we'll use this fact to actually find the electric field in each spot. So we know that due to the symmetry here, it's going to look like a point charge. So we're just filling in to E is equal to KQ over R squared. Because we know that when we're finding the electric field in this problem, it is going to just look like a point charge because of the spherical symmetry. So we know we can use the point charge formula here because the shell theorem says everything looks like a point charge if it's spherically distributed. It just looks like a point charge at the center. So inside the cavity, well, that just looks like a charge of minus Q inside. Inside the shell, we know that E is 0 in a conductor. And outside the system, we said it looks like a 9Q. Negative 9Q, I should say. And again, this is without performing any extra computations because we said it just looks like a point charge. So inside the cavity, it looks like a minus Q. Inside the shell, it looks like 0 because the E field is 0 inside any conductor. And then outside the system, it looks like a negative 9Q. And that's how we do that. So now we'll actually rank the potential inside the cavity, shell, and outside. So to do this, I think it works best just to have a picture. So I would justify this by looking at the sort of downhill definition of how E and V are related. So I would actually draw myself my little cavity here of minus Q. I draw my conductor like so. So we said that outside the cavity, the electric field looks like a point charge. So it would be a sink because it's a negative charge. So outside the cavity, my electric field would look like this, where we have stronger and stronger as we approach the surface. E is equal to 0 inside the conductor itself, because inside, if there are 2 walls around you are both conducting, you get shielded. But then on the very inside, we once again get a field due to that minus charge inside, because that's the only thing enclosed. So this will actually help us, because we're going to rank the field at 3 points, where we have, or sorry, the potential at 3 points, where we have a point inside the cavity, a point inside the shell, and a point outside the system. That's going to be our A, B, and C. So what we're given is that E points downhill. So notice that E is always pointing to the left, or it doesn't have any direction at all. So notice that this means that low potential, the lowest possible potential, must be at point A, because it keeps getting lower and lower and lower as I go to the left or go in towards the center of the cavity. The same argument could be done for any direction in here. So I know that that the ranking of potential from lowest to highest would be A, then B, then C, because the electric field keeps pointing downhill, which would be towards A. There's other arguments, but I like this one the best. Here's my big explanation here. Electric field points downhill, so outside the system, the electric field is in. Inside the shell, there's no field. Inside the cavity, it points in. So thus, the farther in you go, the lower your potential must be. And then we'll graph both of these things, assuming that the shell takes up the distance between R and 2R. So first thing we will do, it says define an outward field to be positive. So we're going to only have negative electric fields here because it's always going to be a sink. So how we graph in physics is what should it do at the start and what should it do at the end. And then we think about connecting. So I definitely know that if I'm getting right next to the charge in the cavity, I need a field that approaches negative infinity. And I also know if I go very, very, very far away from the system, which looks like a negative charge, the field would approach zero. So I also know that my graph should approach zero from the negative side. And then for my connectors, I know that there's something interesting that happens in the region between R and 2R, because that's conducting, and conducting kills all electric fields entirely. So I know that E equals 0 in the conducting shell. So then I can make the following graph, which looks kind of strange, is I know that my electric field is going to approach 0. I guess I could do this better here. The electric field is going to approach 0, but then it quickly jumps to 0. So it jumps to 0 at R, and then it's going to jump back down before decaying back up to 0. So we'd get something that looks like this as our field. This is going to be really strong near the point charge or near the cavity, or near the outside of the cavity. We know the field vanishes inside, and then we also know that it's going to approach 0 in the end. Then for the potential, we just follow the same arguments, where we said that really, really far away, the field has to be 0, and it's going to approach from the negative direction because we have a negative charge system. And the potential gets stronger and stronger and stronger due to the downhill field. But then, as soon as I reach inside the conductor, there's no field or no slope, so I can't change the potential. So again, the field is 0 in a conductor, which means that the potential can't change. The potential can be not 0, as we just saw, but that means that the change in potential is 0 because the field tells you that. And then as we get closer and closer to the center of the cavity, we get closer and closer to that downhill valley. So we actually get this sort of potential graph. There's an alternate approach that involves using the negative integral of E to get V, because V is supposed to be the negative slope of E. And you can see that this is consistent. And it just keeps on giving one more question relating to this charge system. So what if instead we replace the point charge minus Q with a conducting shell holding the minus Q, and then we surround it just with a charged shell of plus Q, creating this capacitor. And it is a capacitor because what we have is two separated conductors of equal charge. So anytime you have two separated conductors, it makes a capacitor. And we'll actually derive an expression for the capacitance of this system by taking the difference in potential between the two surfaces. So a very common mistake here is using C equals kappa epsilon naught A over D. That's wrong. This only applies for a parallel plate capacitor. And this is definitely not two parallel plates. So we actually have to use the definition of capacitance here. By definition, capacitance is equal to the charge you're able to store per unit of potential difference. So what we actually need to compute is delta V for this system. And you could do it two different ways. I think a point charge approach would be quite easy for this, but we'll just show how you do it in general, because what if we had any other system? We want to make sure it works. So delta V can be found by summing up all of your slopes. Because if E is the slope of potential, if you just follow all of the downhill contributions you made in the electric field, you will in fact get the change in height. So for our expression for E, we're going to use E in the middle region between the two spheres. So it looks like a point charge. Because again, anytime you're outside of a system, it looks like that system with all the charge concentrated at the center via shell theorem. So I can just use the KQ over R squared formula for electric field, because it just looks like a sphere or a point charge. And I'm going from R1 to R2. Oh, and I guess in this problem, I should write a negative here, although the sign won't matter, because it is an inward field. So now I could write the delta V would be equal to KQ times the integral from R1 to R2 of 1 over R squared dr, which works out to KQ times negative 1 over R, evaluated from R1 to R2, which can be rewritten as KQ times, well, R2 is the bigger one, so 1 over R1 minus 1 over R2. And we can see that this will be a positive quantity, because the bigger number, R2, is the one that's being subtracted after division occurs. Think 1/3 minus 1/10, that's positive. All right, so now we've found potential difference, which is the most of the work for capacitance, because capacitance is just found by doing Q over delta V in magnitude, where Q is the charge on one of the conductors, and that's just defined as being Q. And delta V was defined as, or found to be, KQ times 1 over R1 minus 1 over R2. And notice that I did say you could have actually figured out the potential using the point charge formula. That's not a coincidence for the sphere setup. Notice it is just KQ over R subtracted. And as always with capacitance, you do see that the Q always cancels. Capacitance does not depend on charge. So we would get 1 over K times 1 over R1 minus 1 over R2, all in the denominator. Oh, that's not what I wanted. You could also have written this in terms of epsilon naughts, which is definitely more common for this problem. If you did this in terms of epsilon naught, you would get 4 pi epsilon naught divided by 1 over R1 minus 1 over R2. That's the same thing. All right, electric field integrals. Here we go. A rod of length L has a constant linear charge density lambda. Consider point P, which is a very small distance A above the rod's midpoint. So first thing is we're going to integrate to find field and potential. So what's important in these problems is starting from the correct formula and making sure all of our distances are in order. So to find electric potential, we can't use a point charge formula because we have to use the fact that V would be the integral of all of the K dq over R's. So we're going to add up KQ over R for every tiny piece of the rod. And we're given the linear charge density is lambda, so we can make the substitution dq is lambda dx, because lambda tells you the charge per length. So if I just multiply lambda by a length, I get a charge. And then for my distance, R, well, I can just pick a random piece of the rod. If I just pick a random piece of the rod, we'll call that distance x, where x is measured from the midpoint. And that would make the distance vector just, or the magnitude of the distance, just the Pythagorean theorem. So now we could just substitute in for our integral. And it says write, but do not evaluate, because these are not fun, nor will they be tested if we can actually do these antiderivatives. So we said that dq was lambda dx, and we said that our distance vector was square root of x squared plus a squared. And I do have my dx already. So we will put proper limits on it. So I will factor out like my k lambda, because those are both constant. And then we'll figure out our limits as I rewrite here. So we have to think about what our variable is. So our variable is x, and x represents the distance from the midpoint. So the furthest left our slice x could be from the midpoint would be half the rod's length, so L over 2, in the negative direction. And then the furthest right it could be would be half the rod's length, but to the right. So this is why our integral gets set up as follows. The harder integral typically is to set up the E field, because E field unlike potential, which is just a bunch of addition of scalars, the electric field is a vector. So we'd have to use the fact that E is equal to the integral of K dq over r squared. So slightly different magnitude. And then we also have to deal with this r hat vector, where we want to extract part of the field. So in our problem, we know that the rod is going to push, every part of the rod is going to push away at point P because electric fields are sources for positive charges. So the electric field, we're going to get all these different contributions where some of the fields are going to point maybe up and to the right, other fields would point up and to the left. Like if I'm looking at this segment would push up and right, but there's an equal segment on the other side that pushes up and left. So as a result, everything would cancel horizontally, so I actually want the y components. So what I want is the actual y components of the electric field. So I'll have to define myself some angle here. I'll call it theta. And I'll need to extract that component in a second here. So same thing as before. We're integrating k times lambda dx is our dq. Our r is still the Pythagorean distance, so squaring it removes the square root. And then what we need is the y component of the electric field. So to get the y component, I see that the y component is touching theta right now. So I want the adjacent side of my triangle, which would be cosine theta. So then, just simplifying, I would get k lambda times the integral from negative L over 2 to positive L over 2 of dx over x squared plus a squared times cosine theta. And cosine is adjacent over hypotenuse, so I get the adjacent side, which was a, because it touched my angle. And then the hypotenuse would be x squared plus a squared. We could simplify this a further step, but as you can see, I ran out of space, and this is a complete answer anyway. So we'll just keep this. You could write it as k lambda a times dx inside the integral, and then your denominator, you'd have a 2 halves power and a 1 half. So you'd get an x squared plus a squared to the 3 halves on the bottom. And it's important that we actually can't use Gauss's law effectively unless if the rod is really, really long, because that would ensure that the field pierces a Gaussian surface cylinder everywhere. So suppose the rod is really, really long. Use Gauss's law to actually derive an expression for the field. So if this is our rod, and we want to find the field a distance a, the trick for Gauss's law for a wire, our magic surface to draw would be a cylinder of arbitrary length. It really does not matter. So this length L of the cylinder doesn't matter, which means it better cancel because I just made this length up. But what does matter is the radius of the cylinder is the point of interest that we want the field at, which is a distance a. So the radius of the cylinder is a. So Gauss's law tells us that the flux through the cylinder, integral v dot dA, has to be equal to the charge enclosed by the cylinder divided by epsilon naught. And if we look, the reason the rod had to be really long is because if the rod's really long, due to symmetry, you actually can't get any horizontal field components. So we get the barrel of the cylinder is exactly pierced by every single field vector. So this allows us to simplify the left side of Gauss's law, which is never the hard part. So never the hard part is the left side. E times the surface area of the barrel of the sphere, which would be 2 pi r, because that's the disk of the cylinder, and that disk is extended a distance L. So that's why we get 2 pi RL for our surface area. And then for our enclosed charge, well, we have lambda as our charge per length, and our length was L. So as advertised, this magic length that we just made up to problem solve definitely canceled. And that's a sign that we're at least doing something right. So now we just divide by 2 pi r, and we get E would be equal to lambda over 2 pi epsilon naught times r as our field. And this gives us our first kind of different electric field from the point charge, where we see if we have a line, which is like a bunch of point charges next to each other, we actually get a stronger field that only decays like 1 over r instead of 1 over r squared, as we saw before. All right, now it's just time to drill a couple more Gausses, and then we'll be out of here. So first, we'll do the insulating sphere, where we have a sphere of radius r, and it has a uniformly distributed charge q, and we want to find the field inside and outside and graph it. So we have this picture where we have a sphere, and the charge is uniformly distributed inside. So we're interested in finding the field at some point inside the sphere. So we draw ourselves a little sphere inside the big one, because due to the symmetry of the situation, we know that the sphere would get pierced by all of the electric field lines, because it would point directly out at all of these points. So that gives us our magic Gaussian surface. It's just a radius r. So we once again know that the flux can be expressed two ways. So the flux, which is the integral of E dot dA, can be found by taking the enclosed charge and dividing by epsilon naught. So in our case, again, it is never the left side of Gauss's law that's hard. I used a sphere, so I'm putting a 4 pi r squared in. And if you forget that formula, it is given to you on the sheet. Then we have to deal with Q enclosed. Q enclosed is usually the one that's not fun. And we already see there's a lot of stuff going on in this expression. So there's two ways of approaching the Q enclosed that I see most often for the uniform sphere. I'll use an approach that's probably the more straightforward one. Other people like this volume fraction approach. We can just use from the definition, since it's uniform charge density, we know the enclosed charge would just be the density times the volume that we enclosed. So for our density, we have a charge Q distributed over a volume 4/3 pi big R cubed. So I'm distributing the charge Q of the entire sphere over the entire sphere. But then for the volume that's being enclosed, it's only 4/3 pi little r cubed. And this should make sense because I'm always going to get a fraction of Q. I'm always going to get a fraction of Q because the little r can't be bigger than big R for the inside the sphere region. And we see a nice little cancellation here where the 4/3 pi cancels. So a lot of people can honestly just see this, and they know this result, that since these both scale with volume, I'm really just taking the total charge and multiplying by this factor of r cubed, little r cubed, divided by big R cubed, which is sort of the charge enclosed fraction, because we know it scales like volume. So that allows us just to write Gauss's law, because we can now say that E times 4 pi r squared is equal to Q times little r cubed divided by big R cubed as our Q enclosed divided by epsilon naught. And then we can simplify by dividing by 4 pi and canceling out two of the r's, and we would get E is equal to Q divided by 4 pi epsilon naught big R cubed. These are all constants. Then times little r. So it actually grows inside the insulating sphere, which is a very important result to remember, that inside an insulator, your field actually grows until you reach the outside. But then outside the sphere, we don't even have to think about it. Outside the sphere, E, it just looks like a point charge from a sphere, kq over r squared. But since I used epsilon naught to begin with, I'm going to use epsilon naught over here. So I'm just going to use the relationship between k and epsilon naught, and just write 1 over 4 pi epsilon naught times q over r squared. So when graphing it, we just look at these functional dependencies. Oh, I almost had something naughty there. Functional dependencies is what I was trying to say. Graph E of r, label all intercepts and extrema. So inside, well, again, just look at our cases first. So we know that if I'm at the center of the sphere, I'm enclosing nothing. So there can't be any charge there. But also I know that in the long term, it should decay to 0. So how this works is we know inside the sphere, we are gaining field linearly because we're enclosing charge at a cubic rate, but area is only increasing, or distance is only increasing at a quadratic rate. So we get a net change of linear growth. But then once we reach the outside of the sphere, we have stopped gaining charge, so it decays via the inverse square law. So this would be, in terms of our labeling, inside the sphere, it's proportional to r to the 1. Outside the sphere, it's proportional to r to the minus 2, inverse square. And then the maximum value is just when it looks like a point charge at the surface, which would be kq over big R squared. So that's the insulating sphere of uniform density. Of course, we also have to do the parallel plate. This one is definitely not bad. It's just a weird derivation if we've forgotten it. So a plane of charge actually generates this sort of uniform field. And the trick for the plane of charge is drawing any surface with whatever area you would like that's symmetric about the plane and goes sort of above and below with uniform cross-section like this. So as we can see from this cylinder that's drawn, actually that is horrendous. Let's redraw that. So I'm going to draw myself an attempt at a better cylinder here. Yeah, that's a better attempt for sure. So it has area A. So if I just draw myself any cylinder, we see that the cap of the cylinder would get pierced on both directions by the electric field pointing directly out. So both of these caps of area A would be getting directly pierced by the field. So when writing Gauss's law for this, of course we always start with the integral of E dot dA, which is flux one way. It can also be written as flux the shortcut way as Q enclosed divided by epsilon naught. Well, for my flux, I see that I have an electric field E, and we know it should be equal due to the symmetry, that E should be the same at both the top and bottom because I drew a symmetric surface. So I should get an E penetrating an area of 2A because the top and bottom cap get pierced. And then for my enclosed charge, it's given that sigma is charge per area. So I have sigma charge per area times an area of A enclosed by the cylinder. So again, the reason I use A and not 2A for the right side of Gauss's law is because the only thing that the plane is getting pierced by is the 1A. There's only this cross section right here that's actually getting charge from the plane in it. So I only use that A there. And we see that A was totally arbitrary and I made it up, so it better have canceled, and it did. Because I have A on both sides. So this allows me to write that the electric field from an infinite plane is, as advertised, sigma over 2 epsilon naught. So now we're going to look at the field from two parallel plates, which is of course very important to us with capacitors. So if I have a positive plate and a negative plate, we're interested in the field between the two regions. So if I'm between the two regions, the positive plate would try to repel towards the negative plate. And if I was between the two plates, the negative plate would attempt to attract. So notice I actually get two fields that are adding in the region between parallel plates. So E between the plates would be 2 times E from one plate, which would be 2 times sigma over 2 epsilon naught, which would be equal to sigma over epsilon naught. So that's one way of writing the electric field between two parallel plates, but it's actually not what the answer wanted us to write. It has Q and A in there. So to do this, we just use the definition of sigma, where since sigma was Q over A, by definition, we could write E is just equal to sigma over epsilon naught, which is Q over A, divided by epsilon naught, or just sending the A on the bottom to clean everything up, we get Q over A epsilon naught. All right. So now we're going to talk about the main features of the field setup between two plates. So we've drawn the setup over here. So we also see that outside the plates, the positive would push away. So using my source and sink rules for positives, I just keep making the positive go away. And then the source rule and sink rule for negatives. Again, negatives, it always points towards a negative plate. So what we can see is that outside the plate on the top, we'd get 0 field because the plus and minus cancel. Below the plates, the plus and minus fields cancel. But in the middle, we'd get sort of 2 times the field from one plate. So that's kind of the behavior of the E field between parallel plates, is it's 0 outside, and then it's twice the field from one of the plates inside. So we get a constant field of magnitude Q over A epsilon naught, and E0 outside. Now for the potential difference between a set of 2 parallel plates, we could use the fact that delta V is equal to the negative integral of E dr, or we use the fact that since E is constant, so if E is constant, we can actually simplify this to not use an integral at all. So this only works with a constant E field, but if you have a constant E field, you can pull E out and you're just integrating the path length. So for constant field, we can write V is equal to E times D. So in this case, we can just write that the magnitude of the potential difference is just going to be E, which was not sigma, we want Q over A epsilon naught, and then D, which would just be QD over A epsilon naught. So that would be our potential difference in magnitude between the 2 plates. And now we can derive an expression for capacitance, because we're given that capacitance was equal to the charge stored per unit of potential difference. So our charge was Q, but our potential difference was QD over A epsilon naught. Charge cancels once again, so we get the familiar A epsilon naught over D formula that gives us capacitance for parallel plates. We're missing a kappa, but the kappa just effectively increases epsilon naught to some other value. All right, and then to finish, we have the non-uniform charge density version of Gauss's law. So we have an insulating sphere of radius r, and we get a rho of r. So to do this problem, we're going to use the fact that Q is equal to the integral of rho dV, but that doesn't mean just integrate rho, because dV is about the change in volume. So the shape matters here, and the fact that it's a sphere tells us that we multiply by 4 pi r squared dr, because that's our surface area times our thickness. So this is our relevant formula. So first we just want the total charge in the sphere. So the total charge in the sphere, Q total, would just be integrating rho of r times 4 pi r squared dr all the way out to the sphere's radius. So our expression for rho of r was just given to be br to the 4th. And then if we evaluate this, we would get 4 pi b times the integral from 0 to r of r to the 6th dr, which evaluates to r to the 7 over 7. So I get 4/7 pi b big R to the 7th. So not a very nice expression for total charge. All right, now find expressions for electric field inside the sphere and outside the sphere. So first inside, we're once again just going to use Gauss's law both times. And I know that this has spherical symmetry, so the left side, even though the problem is a lot harder looking, we never have issues with the left side of Gauss's law. Always get that point for yourself. And then for our enclosed charge, we said that the enclosed charge was 4/7 pi b big R to the 7th. That would be for the entire system. But if we just wanted any point, little r, we could do the same thing. We could just replace the big R we found in the previous part with a little r. And then that's basically done. We just got to simplify. So actually the 4 cancels, the pi cancels, 2 of the r's cancel. So we get E inside the sphere would just be equal to br to the 5th divided by 7 epsilon naught. And this actually follows our little theorem that inside an insulator, the field is always 1 power of r greater than the charge density. So br to the 4th, I should have a br to the 5th somewhere in my field, which I do. All right, then outside the sphere. So outside the sphere, it just looks like a point charge. So I just know E would be equal to K times Q total over R squared, because we're outside the system, so it just looks like a point charge. And then our expression for Q total was 4/7 pi b big R to the 7th divided by little r squared. And if I were to simplify this in terms of epsilon naughts, I would get b big R to the 7th divided by 7 epsilon naught little r squared. So it is inverse square, because that big R to the 7th is a constant. All right, that was a lot, but we made it through all of electrostatics.